Well, good morning, everybody. David Barber from Washington, DC, where it's currently snowing, so the whole city is shut down. So it's a bit of a shame. First of all, I'd like to thank Scott and WoodWorks for allowing me to present this morning. I'd also like to thank Bevan for getting you all tuned into the New Zealand accent. So that means everybody will actually understand every word I say, which doesn't always happen. So thank you. Thank you, Bevan. Sorry, before I do this, Carl mentioned this before as well. This is an image of a very close-up image of a piece of CLT that's gone through a 2-hour fire test. And as you can see, the char has moved through, and this has a pointer, maybe? Oh, there it does. That's the line of adhesive right there, and it's charred right through that line. And that is the difference between char falloff with CLT and not char falloff. So this piece of CLT, the charring has moved right through and there's no char falloff. And the reason that's important, we'll go through into this presentation. And char falloff is often called delamination. So we'll find out a little bit more about that. I always like to start with a little bit of history because I like building history. And the reality is that we're talking a lot about future code changes as to where we are going, hopefully, with tall wood buildings. The reality is we used to build tall wood buildings. This is in Minneapolis building, which was finished in 1906. And there used to be a lot of taller wood buildings around globally, quite a number in the US, quite a number of Canada. And they started to be pulled down in the 1920s and 1930s, mainly because there was this cool new material called concrete that came along, and everybody wanted to build in that because this was kind of so last century. So the reality is that we're kind of in a new century and we're looking at doing something like this again. But I think when it comes to these code proposals to look at taller wood buildings, we've also got to be realistic about the fact that we have done this before. So we should get reasonably excited, but also we should be realistic about the fact that this is not new, and we have built successfully taller wood buildings in the past. So it's kind of nice to think of it like that. Mass timber, glue lam, cross-laminated timber, and nail laminated timber. I'm going to talk a lot more about CLT and aspects of exposed mass timber, especially in high-rise buildings. I normally talk a lot about glue lam because that's sort of my sort of background as such, but it's great to be able to talk about CLT, which is another really interesting product. These very cool buildings here, one on the left-hand side for yourselves, that's about 16 years old, was built in Austria. This here is close to 20 years old, is in Norway. That's not actually a black and white photo, that's just some very cool Norwegian timber design, and they've let it age. And you can see a little bit of red there, but I mean, you can get away with that in Norway because it's very cool. But the reason these are in here is because these are old CLT buildings. And one of the perceptions is that CLT is very new. Compared to glue lam, glue lam's about 125 years old. You know, CLT is about 30 years old, so relatively, it's kind of, it's newish. But we have been building for CLT for quite a number of years. We know about how it works from a durability point of view, vibration point of view, from a fire point of view, and especially from a strength point of view. So we're continuing to use the technology and find out different ways to be able to use it, but the reality is we've actually been building for it for quite a long time. We just haven't been building with it here in the US. So when we talk about the newness of the material, it's kind of newness to the market rather than newness of the material. And I think that's one of the real perceptions that goes on with CLT that I constantly have to try and correct people on, is the fact that yes, it is new here. It's kind of nice that it is starting to take hold here in the US, but it's actually not a new material. And it's kind of nice to see buildings which have actually aged and got sort of all, the silver tones of very aged timber. It's very nice. And of course, CLT buildings are getting constructed different parts of the world, different heights, and we're seeing residential and office buildings going up, and the reality is that all these different buildings have different codes that are associated with them. And so with different codes, there comes different requirements. And so often we see people looking at buildings overseas and saying, well, why can't we do exactly that? And the reality is that each code has different sort of intricacies, as we all know. And so that means that in certain parts of the world, you can do certain things, and in other parts, you can't. And I think when it comes to CLT buildings and mass timber, and generally mass timber and high-rise buildings, we need to be respectful of the fact that there is going to be a code environment we have to start with, and we kind of have to fit the timber into that and then move it sort of sideways. And we're starting to see that with the work that's going on with the ad hoc committee, which has been, they've done some fantastic work to be able to sort of start to move everything in the right direction. But the reality is we're starting off with a base, which is the fact that we start off with a code which is material based. So when it comes to heights, it's based on the material you're using. A lot of these buildings which have been constructed in other countries have a code which is not material based. So it's more about the ability to achieve a fire rating 1 hour, 2 hours, 90 minutes, whatever it may be, irrespective of the material. So there's often quite a lot of difference just in that itself. So from a CLT point of view and a mass timber point of view, our code starts to set the direction which we obviously then need to follow. I think another issue from a perception point of view is how, in some ways, mass timber is kind of marketed. And this is the Brock Commons building. And if you go online and search under Brock Commons and look up the images, you see a lot of images that look like the one over there, in that corner up there, that look like this. You see very few images of what the building actually looks like when now it's actually been tenanted, which is, and people, students are living in here. People, students, yes, they are students, they are people. And the fact that it's fully enclosed and fully encapsulated. And so you see all these very cool photos like this, and some with the mountains in the background and the lake and those sort of things. But the reality is that it looks good from an architectural point of view, and often we see the mass timber, but when we want to use buildings and use them in a way which allows them to be very durable, allows them to be maintained in a very relatively cost-effective way, covering up all the mass timber and actually having a drywall finish is actually quite reasonable and quite a sensible way to go. And so the process from Brock Commons' point of view of actually covering up all the CLT and the glue lam and actually having something which is very livable and usable from a university's point of view is helpful. But I think there's also this issue that, as Carl touched on, we see certain parts of the industry wanting us to drive towards having a lot of exposed timber. And there are other parts of industry that are very concerned about that, and actually from a safety point of view, but also just from a usability point of view, that actually having things partly covered up or mostly covered up is actually kind of sensible, because there's a lot of stuff which goes on in buildings that you probably don't want to see. So there has to be a middle ground, and I think at the moment we see a lot more imaging around this and a lot less imaging around this, but the reality is that mass timber buildings are, once you get to sort of 18 stories, are a success story. So we have to celebrate that aspect, but we also got to be respective of how the building will be used. Certainly this year there's going to be 2 buildings that are going to be constructed, which are very much high-rise buildings. The framework building in Portland, which will be sort of a 10-minute cab ride across the river, will start this year. That's 12 stories, and it'll be a great building to see being constructed. And just to plug, straight after lunch, I'm doing a presentation on the framework building and the fire tests which we carried out on that. We've never been able to talk about the fire tests previously, partly because of the way that we were going through the building permitting and those sort of things. Now that we've got a building permit, I've been allowed to talk about the fire tests. So if you want to find out about those, come and see the presentation after lunch. And this building here, which is in Amsterdam, I wanted to show this simply because this is a great rendering, but the building doesn't quite fit the way this rendering looks, because when you understand what this building is, first of all, this isn't a high-rise building. This is a 20-story building, but under the City of Amsterdam code, this is not a high-rise. So that's one of the things about codes and how they work. It's true, it's not a high-rise building. It caps out basically about just basically at the height of this building. This building also has concrete, steel, and CLT. The cantilevers in here, which are great CLT cantilevers, primarily are steel structure. There's a whole lot of concrete shear walls in here. And so I think, when we see buildings like this, we have to understand the fact that often they are hybrid buildings. Often there's a whole lot of stuff that goes on behind the scenes that often we're not aware of. And again, with this building here, there'll be certain levels of protection inside here where the CLT will be uncovered. Some of it won't be, some of it will be protected. And so how we see those buildings is also important, because what we often get, or what we often read and get from the images we see is a certain message, but actually the engineering and the approvals and those sort of things give us something else which is quite different. And again, it's that aspect of how these two come together such that we can actually understand how we can build potentially a building like this here in the US. And of course, the framework building is something which is a lot more transparent, and especially through the Tallwood design competition, everything will become very transparent on that building, which allows it in some ways to be copied, which was the original aim of the Tallwood building competition. So once all the documentation comes out on that, there's the ability to be able to understand how to replicate that building, which is very different to a building like this, where as a private building, most of that information won't be actually in the public domain. So exposed CLT and exposed mass timber. What I want to talk in this presentation really, and this came about from a discussion with Lisa Podesto quite a few months ago about the issues of CLT and mass timber and exposing it in high-rise buildings, and how do we explain the issues associated with that. So in some ways this is a very technical presentation which I've tried to get down into around 15 to 20 minutes and explain the issues that are associated with this. But then the two aspects are really related to fire resistance ratings and compartment fire dynamics. Luckily, Bevan's gone through fire resistance ratings already, so I don't need to go through that in a great deal of detail. But I will talk through what the mass timber aspects are when we have exposed timber related to that. And most of the exposed mass timber I'm talking about is CLT. In most of these spaces, we're going to expose the CLT. The second part is compartment fire dynamics, which is a nice term that us fire structures people like to talk about, which is the space where the fire burns. So if you've got a residential apartment building, it's primarily the space where all the fire can burn in between the fire separating walls and the two floors. And if you think about an office building, it's pretty much the whole space inside the office floor in between those fire-rated floors as such. So that's kind of the compartment. And so the first thing we have to understand is what is a fire. And so for looking at a residential case, we have to understand what the actual fire is in the way that it burns. And the way that we test things and understand things from a structure's point of view when we apply the fire is we assume that the sprinklers don't operate and we assume that the fire department don't intervene. Very, very extreme case. And we do this primarily for high-rise buildings. And this is consistent for codes around the world, is that once you get to a high-rise building, we assume no sprinkler activation, no fire department intervention, so we have a fire that grows and burns out. And this is what a fire looks like in a residential apartment. This was a fire which was carried out at NIST, and this is what the curve looks like. It goes pretty steeply. Once we get all the foams and all the plastic starting to burn, you get sort of a steady sort of period of growth once all the sort of wood furniture, which was kindly provided from a Swedish homeware manufacturer, into the space. And then you start to run out of fuel and you die down, and the fire basically decays down into not much. And this is what the fire size looks like, which doesn't really mean much to most people, but temperatures we can all understand. So this is what the temperatures look like within the space. And as you can see, you get sort of growth up, which kind of matches the way the fire grew, up to about 1100 degrees Celsius, which is about 2100 Fahrenheit. And then as the fuel starts to dry down, you basically get decay into the fire and then it sort of dies off. And the scale down here is, up to sort of 3 hours. So for this residential apartment, that's what the fire did. And this, as I said, is based on the fact that we don't have sprinklers and we don't have fire department intervention. So what we do as engineers is, we approximate this. We take basically an average of all the information that we get out of this and we create a curve which basically allows us to model what's going on in this apartment. Because what we want to do is take this direct information from this fire and be able to use that to understand if we want to model a different fire in a residential apartment or a different sort of space. So if we want to change the ventilation, change the floor area and those sort of things, we understand what the floor load is so we can sort of replicate that over a certain area, and then we can actually carry out some analysis on that. The important thing is that if you're going to have fire ratings in a building, a 1 hour rating or a 2 hour rating, the way we do that is we test materials to this curve here. So this is the standard fire curve, ASTM E119, and it looks like that. And as you can see, there's quite a difference. It grows a little bit more slowly, but it's sort of slowly keeps on increasing. Once you get to about sort of 2 hours, you're roughly about sort of 1100 degrees, which is kind of what the compartment temperature is at about 2 hours. So as you can see from that, what we're looking at is two different types of fire curve. One is the standard fire curve that we would test a floor or a wall or a beam to get the 2 hour fire rating. The other is actually what's called a natural fire curve. So it's a sort of fire you would get if you have a space, you set fire to it and you record all the data. And so as an engineer, we need to understand both of these fires because the way that we put structure into a building, it's tested to this black curve. That's what it's designed to and tested to, and we install it. So we install a column, we install a beam, we install floor and wall systems, and they have a testing to this curve. But when we have an actual fire in the space, we're going to be having an exposure that looks something like this. And there's a difference between them, so we need to understand both of those. So why is that important for exposed timber? Well, if we have an apartment, something like this, a residential apartment, there's a nice dog down the bottom here, it has a little bit of exposed wood here, but we know that if we model that apartment, we're going to get a curve which looks something like this. It grows up and decays, as I said earlier. And we know that we've got structure which is going to be tested to this curve, and we know that provided our heat, all our heat release is releasing enough energy that it's less than the total amount of energy that the structure has been tested to, then we're going to be okay. So it's an energy balance. Our structure has been tested to withstand a certain amount of heat energy. We've got a certain amount of energy in this fire, which is going to be in the space. We know what the fire load is. We know what the ventilation. Provided that fire was releasing a lot less energy than this fire, we're okay. And that's the way basic structural fire analysis works. And that's primarily what we do for high-rise structures. And so importantly for us, for a 2-hour rating, is we need to understand what that means at 2 hours. So we expose a bit of mass timber. We expose some CLT here in the ceiling. What does that mean? Well, the first thing it does is basically introduce more fuel load because we're introducing more combustible items into the space. So it changes the way that the fire curve works in this apartment. And we can model that. And we can understand what the difference is in here as we expose this mass timber. And so we still, again, have this energy balance. We want to make sure that we're releasing a certain amount of energy, but that energy is a lot less, again, than what the construction can actually withstand, what the beams and columns can withstand. And again, we need to understand that at 2 hours and make sure that that energy balance works. So if there's a certain amount of mass timber we can expose, if there's a certain amount of CLT we can expose and know this is still going to work. But we expose a whole ceiling like this, a whole lot of mass timber. What we start to do is push this curve a long way out. And so what we're doing here, as you can probably realise, is we're releasing too much energy into the space. There's too much heat energy, and so potentially what we can do is when we check where we're at 2 hours, is the fact is that we've got so much combustible fuel in the space that we're potentially overrunning the fire-rated construction that's been built into that space. And so that's an issue for us. And so when it comes to exposed mass timber, exposed CLT, the first thing we have to assess is the fire rating, is to understand this energy balance. And so that's the first thing. And it's an important aspect, and it means that there is a certain amount of mass timber, CLT, that we can expose in a compartment, but there's also a limit to that. The second aspect is this, char falloff, and this was mentioned earlier before, and you may hear this a few times, often called delamination. And the easiest way to see this is 2 fire tests carried out here in the US on 2 different types of CLT. Both of them are fairly similar in their production. The difference between the 2 is the type of adhesive. And this one on this side has not shown any signs of char falloff. And this one, it's a little hard to tell, especially if you're in the back of the room, but there are areas where the char has fallen off. And the reason that that's important is that, as I said earlier, and showed this image earlier, is that if the charring burns through and the char stays on, what happens is that we get charring like normal wood. So it's just like any other piece of glulam or solid timber. If we have the situation where, because of the adhesives, that the char starts to fall off, we have this issue whereby once the char drops off, we're getting a little piece of wood which is exposed to the fire, and that has lost its protection. The char is simply protection, so it's kind of lost its fire-rated material which sits below it. And the reason that this is kind of important is the fact that there's 2 things. First of all, this graph's showing the charring rate. This little line showing the charring rate and this little schematic of a piece of CLT. And so timber chars through at a normal rate, and then if it's got a propensity to have char fall off or delamination, you get this increased charring rate or increased burning rate as you reach that glue line until the char has built up again, and then you reach again this normal charring rate until you get to the next glue line, the char falls off and you get increased charring rate or increased burning rate. And it's that increased burning rate which is the key thing here, because what that's doing is, if you can imagine there's a piece of wood which was protected, then suddenly the protection drops away, it is exposed to a lot of heat, it starts to burn and burn relatively quickly. What that does is it has a change in the actual char rate. So if this here is the standard char rate, this here is a whole lot of pieces of CLT with adhesives which actually have the ability, they allow CLT to actually delaminate. You get this variance in the actual char depth. So what that potentially means is that if you've got a piece of CLT that delaminates, you're going to have to use more depth of wood to actually achieve the same fire rating as one that doesn't. So that's one aspect, so you're actually using more timber. And this graph is actually from some testing that was carried out probably more than 10 years ago in Europe, so it's not something we've known about for quite a long time. That's one aspect. You can in some ways you can kind of say, well, we have to use more timber if we have delamination. So what? You know, in some ways that's not a big issue because it's not a significant change. But the other issue, which is probably is certainly more important, is this here. And this is this aspect of the increased burning rate. Once the char falls off, we start to get this issue of having the wood starting to burn. And you can see that here, and this is part of the NIST test, and you'll see a lot more about this after lunch, and Joseph's going to have a very good presentation on this. 2 hours and 7 minutes and 2 hours and 14 minutes. There's a difference here in 7 minutes, and there's some other images of this later on. You've got the timber starting to have some char fall off and the fire starting to increase, and then same space, a little bit later, it's starting to grow quite a lot more. And that's the issue of the char falling off and this burning rate growing. And so that's important, because what we want to be able to do is make sure that we have fires which continue to decay as all the fuel starts to run out. And in this space here, there's not much fuel left. All the combustible furnitures have all burnt down. There's just a little bit of heat exposure to this wall. But what's happening is if the char falls off, we're starting to get this burning starting to increase, and then that burning starts to sort of play on itself. We get one piece that's infected by its neighbour, more and more of that occurs, and you get an increase in the actual in the heat output. And again, this is just showing what can happen if you have things go poorly for you in this sort of testing, and the fact that you get a peak burning as such, you get a decay, and then what normally would happen is this would just decay all the way out. But if you start to get the char fall off, potentially you can get growth. And this fire stopped here, but the reality is this would grow and then probably decay again. And the problem with that is, from an engineering point of view, is that this here is unpredictable. And we can't predict that with a great deal of accuracy. And so from an engineering point of view, we want to make sure that we can predict everything very, very well. And so we can model this and we can engineer this very well. We can't model this that well. We can try, and there's people at the moment doing PhDs to understand how to do this pretty well. The reality is the best way to be able to make sure that we can determine how best to make this work in buildings is to actually avoid it. And that's what has occurred through the testing that NIST carried out, and these large-scale tests which the ICC helped carry out as well. And as a result of those, where there was exposed limited areas of ceiling, as I talked about it earlier, it's about trying to have a certain limitation on the amount of exposed wood we have, and understanding how exposed walls can impact on the fire. We can then start to draw some conclusions. And one of those is that we obviously need to maintain some surety in the way we actually carry out the design. So when it comes to mass timber, there's a couple of aspects here which I think are important just to finish on. First of all, for buildings less than 85 feet, we can have exposed CLT, and we can do that completely appropriately because the code allows us to do that, which is great. For high-rise buildings, exposed CLT is okay, but in limited areas, and we need to understand what those limitations are. We need to understand and work through how much wood we're actually exposing, how much CLT we're exposing, how that impacts on the fire resistance ratings. CLT walls will have lesser impact than CLT ceilings, and that's pretty obvious because we have a lot of hot gases and fires at the ceiling rather than at the walls. The adhesive used in CLT is important, and as a result of all this testing, there has been changes to PRG 320, which is the manufacturing standard, and that's been a significant importance to try and make sure we don't have this char fall-off issue. So we can take an engineering problem, a problem of uncertainty, and remove that from the equation. So it allows us to model things very accurately. And so last thing is, where CLT is not exposed, we need to protect that and make sure that it doesn't char. So we need to actually understand how to protect the mass timber, the part of the timber that's actually combusting, and make sure that we stop that burning. So there's certainly a few other aspects to how we control mass timber construction, CLT, within fires and within high-rise buildings. So with that, thank you very much, and look forward to, I suppose, a few more minutes of questions. Thank you.
Thank you.